In this lesson, we'll be implementing spotlights. So a spotlight has position, but it also has a specific direction. And since it has position, we know that it can also have attenuation. And because it has a direction, we can also implement the idea of a flashlight concept where we have an inner angle and an outer angle, and the light can attenuate not just with distance from the surface of the object to the light, but can also attenuate outside of the cone, from the inner cone to the outer cone. And here's an illustration that kind of demonstrates that. We can have a sphere of influence around the light itself, where the light has a position in world space. That light can also be modeled with a direction, the red arrow here. So we're looking in a specific direction. So a little different than the point light where it casts light in all directions. Here, it's casting light in a specific direction, but that light can attenuate according to an inner angle and an outer angle. So that's what we're going to implement here in this lesson. Back into Visual Studio, and let's take a look at the Spotlight Demo.h. So the Spotlight Demo class has got a Spotlight instance, and that Spotlight instance combines the components of the directional light and the point light. So it inherits from point light. I could have just as easily inherited from directional light and then added the point light pieces in. So I'm inheriting from point light, and then I'm adding the directional light components to that. And that includes apply, rotation, and then adding a couple of additional members for an inner angle and an outer angle. The rest of that implementation for apply rotation is identical to that of the directional light. Now you might be thinking, well, why not use multiple inheritance to do this? I tend to avoid C++ multiple inheritance, but if you'd like to use multiple inheritance, inherit from both point light and directional light, you're welcome to do so. Okay, so back in the Spotlight demo, let's look at the Spotlight effect. That's our new shader program. And it still has a world view projection and a world matrix and an ambient color, light color, and we have a light position and a light radius. These two things are associated, right? So that's that sphere of influence is the radius around the position. Now we have a new light look at, and that corresponds to this image's direction vector. So which way is the light looking? We also have the Spotlight inner angle and Spotlight outer angle variables. If we take a look at the Spotlight vertex shader, you can see where a few of these are declared inside of the shader. So we still have an attenuation function. We're going to calculate the attenuation in the very same way. And now we're passing through the light look at. And the reason that we're passing the light look at in from the vertex shader is so that we can invert it, right? Assuming that the light is coming in from the perspective of the spotlight and not from the perspective of the surface to the light. If it did, of course, then we could skip this step and we could read the light look at uniform directly in the fragment shader. Otherwise, this code is the same as the point light shader. Now let's look at the Spotlight fragment shader. So there's a lot of different stuff going on here. This is a little more complicated than the last one. Here we've got a Spotlight inner angle and a Spotlight outer angle, and they're initialized to the values 0.25 and 0.75. Now, I don't want to confuse you and say that these equal signs means that this is hard-coded, this is a constant value. Not at all. You can pass in new Spotlight inner angles and outer angles. But if you don't specify them at all, we can default them. We could have done that for all of these variables. Now we can see the VS output structured with the light lookat member included. And you can see that we're computing the light direction vector and the view direction just as before. All of this material is identical to the previous shader, except for now we've got a light lookat that we're renormalizing. So again, remember we talked about normalization coming out of the rasterizer stage, coming out of the interpolator, might not be normal. In fact, it may not have been passed into the first place as a unit vector. Now we're just guaranteeing that the light lookat is a unit vector. So we compute the ambient and diffuse exactly in the same fashion, and we compute the specular highlight in the same fashion. But what's a little different this time around is now we're going to compute a spotlight factor, and that spotlight factor is computed similar to how we did the dot product between the normal and the light direction to compute the diffuse value. Well, now we're going to compute the dot product between the light lookat and the light direction. So that is the direction that the light is looking. And now the light direction that we've passed in is that light position minus the world position. So I want an angle from the center beam to where the actual position of the light is. And that spot factor then, if it's greater than 0, to compute a spot factor, and this is the HLSL smooth step, and this smooth step just gives me interpolation between these two values. The GLSL smooth step intrinsic says I want some of the value to come from spotlight outer angle and some of the value to come from spotlight inner angle according to the light angle. So if the light angle is 0.5, then half of the value will come from here and half the value will come from here. Let's make sure we understand what this concept is. That spot angle then, that spot factor, is computed somewhere between these two values. So let's say that they weren't passed in from the CPU and they just had the values that were defaulted here, 0.25 for the outer angle, 0.75 for the inner angle. So now my value is going to be somewhere between 0.25 and 0.75. And what I'm going to do is multiply that spot factor. And let's say that it was fully inside of that narrow beam, so it's in the inner angle, then it'll be 0.75. And now I'm going to multiply that spot factor by the addition of the diffuse plus the specular. So all I'm doing here is now modulating the final influence of the light depending on the orientation of the light with respect to the position of the light. So the orientation of the light and the light direction vector. And something else that's very interesting about this is that if I set these values to be, say, 1 and 0, now I'll have a nice, real smooth interpolation between the inner angles and the outer angles. If I set them to be the same, for example, 0.5 and 0.5, then as long as my light angle is greater than 0, I have some sort of spot factor, and it'll always be 0.5 if those two values were the same. I'll show you that in the demonstration here in just a moment, and you'll see where that creates a hard edge around our spotlight. So let's go back into the spotlight demo implementation, and you'll see that we're compiling that shader. We're building up a quadrilateral here instead of a sphere. The same quadrilateral that we had before in our texture demos. And now we're going to specify a checkerboard pattern as the texture and instantiate a spotlight. And our spotlight's going to have a radius of 500, so it has massive influence. Let me drop that down. I'll drop it down to, say, 50. So you can see the attenuation in action as well. And we're going to give an explicit position right off the bat. Now, our spotlight proxy object, we're going to make that proxy object a scale of 0.5. It's a little big, so I've scaled it down to 0.5. And initialize it and rotate it as well. So our spotlight proxy is going to look like a cone. So it has real rotation. And just like with the direction vector, I needed to rotate it so that it aligned with our arrows. And when we update the spotlight, and that's what we're going to look at next, is this update spotlight function. When we update the spotlight, we have an intensity that we're going to do with the home and end key again. And we have the moving the light around, which we're going to do just like we did with the point light. You know, the IK and the JL and the N and M keys. But now we can also rotate the light. And the way that we'll rotate the light is we're going to rotate it with the left, right, up, and down keys. So the arrow keys. And with the V and the B key, just as with the point light, this will change the radius of the light. Finally, we want to update the inner and outer angles. And we'll do that with the Z and X keys and the C and the V keys. I encourage you to explore this code a little bit further if you want to see how this is done. But this should be pretty old hat now. This is very, very similar code that we've been just adopting over and over again and changing just a little bit to suit the specific demonstration. So back in the draw code, this looks awfully similar now. And that's what's great about this syntax, in my opinion, is that it makes the use of the shader pretty easy. You can pass data in without having to reinvent the wheel over and over again. So it's very consistent, very easy to identify. You know, here we're abiding the vertex and index buffers, setting this shader to use, and now we're passing in variables. And, you know, something that I haven't talked about too much is that we have to do this every draw call. And you might ask yourself, why, if I only have one component that's being drawn? Well, that's the idea, is that you might have lots of components that are being drawn. So every time you change states inside of the OpenGL pipeline, those states stay the same until you update them again. Let's say this particular shader is being used by multiple objects. Well, of course, each one of them will have different settings. That's why we need to update these per draw call. You could do a little bit of testing there. This as well. Maybe, you know, this thing hasn't changed, but truly you need to update these every draw call. And now we're going to specify the color texture just as before and the GL draw elements to draw the quad. Let's run the application. Let's see what we get. All right, so there's our quadrilateral. And there's our proxy model for spotlight. Looks like a cone. So I'm going to move this around. I'm going to position it pretty close to the screen just to kind of amplify the effect. So I'm just using the I, J, K, and L keys to move this around, and the M and N keys to move it into and out of the screen, so along the Z-axis. And notice then, when I rotate this around now, sure enough, it behaves like a spotlight should, right? It behaves like a flashlight. So that's pretty interesting. We can change the intensity of it by pressing the home and N keys, right? So I still had specular on there, which is why you still see a bit of specular. I can turn that off. But now that's just the spotlight. And the spot factor that we talked about, you can see that in action as the surface normals face further and further away from the lookout of the camera. The camera is facing this direction. Well, now these surface normals are almost perpendicular, and these ones are or are behind in the opposite direction of that light direction. So when that happens, that's what we're going to do, just like Lambert's cosine law. Okay, so the last thing I want to show you here in this demonstration, let me turn this up a little bit more and get kind of close. The last thing I want to show is that X and Z, now what I'm doing there is I'm pressing the Z key and the X key to modify the inner angle of the light. If I specify that to its minimum value, I've clamped that to a specific value. Notice what I can do when I press the C and the V key. With the C key, now I have a very small field of influence. I can increase the size of the influence by specifying a larger outer angle. And watch what happens now if I change the outer angle and the inner angle so that they're the same values. So now I have a very harsh edge, and this could be used for a very, very hard-edged light. And then this creates a softer edge by interpolating between a greater range. So that's all that's going on there, is we're just doing interpolation between the inner angle and the outer angle. And we can also see the impact of the light's radius. As I pull back from the light, we should see attenuation happening here. I think my radius might be really, really far, so the further I get away, now the light starts to attenuate. So I can change the range, I can update the range at runtime, and as I get closer to the object, between the light and the object, then I have more influence from that light, and as I get further away, then I have less influence from the light. So you can see that this attenuates just like a point light, but it also attenuates along the look-at vector of the light. All right, that settles it for spotlights, and that wraps up our discussion of basic lighting models. And in the next lesson, we're going to talk about some more advanced rendering techniques.